Okay, sorry. Okay, so it's a kind of new improved version of what we did together. So it's on distributed Monte Carlo and with application to large-scale based inference. So, okay, so where we cover first what is the problem behind this is the problem of representing uncertainty in machine learning. So there are many ways to do that, of course, but the thing that you need to be known is that representing uncertainty is really critical to decision making. And one of the problems which has been identified by many researchers is that machine learning model, and especially deep learning models, because deep learning have many parameters, sometimes several billions of parameters, they typically lack a representation of uncertainty. And what has been often reported, and I will give an illustration on a vision task, is that machine learning problems are extremely accurate compared to many classical machine learning algorithms, but they are most often overconfident and generally miscalibrated. And in general, they are overconfident. And so there is a kind of objective which is shared by many researchers and many streams of research, which is the ability to quantify uncertainty in a trustworthy way. So I rephrase what Herman said, is that methods for reasoning and making decisions under uncertainty are important building blocks of accurate and reliable machine learning systems. And in many applications, ranging from supply chain planning to medical diagnosis to automatic driving, faithfully assessing uncertainty is very important, is as important as obtaining high accuracy. Okay, what is a classical supervised machine learning problem? So what you do, you start with a train set with an observation. So in many examples that I will take a classification task, a supervised classification task. So you have a response, yi, which is called also the dependent variable, which takes typically value in a discrete set in the case of classification, or continuous state in a kind of a prediction. Problem, as I said, most of my example comes from classification problem, and xi are the vectors of features or attributes or independent variables. And what you do in supervised learning is that you have a statistical model. The statistical model is simply, in probabilistic world, it's a conditional distribution of the dependent variable given the independent variables, and this quantity depends upon some parameter theta. In most of the example I will use, this model will be, in fact, done with a deep net, so convolutional network, Bayesian network, something like that. And what you do when you do parameter estimation, you solve the supervised learning problem, and supervised learning problem is simply penalize maximum likelihood. So you maximize the likelihood of the observation of the, and then you might add a penalty. And in the deep learning case, the penalty is typically the square norm, something very simple. Sometimes it's sparsity inducing quantity, but most of the time it's a very simple regularization, and you end up with predictive distribution. When you apply this to a vision task, and this is an example which has been done by Vincent, but you will see the similar example in many publications. So you look at the label, and you look at the what are the label which has been predicted, and you look at the confidence of the prediction as expressed in terms of the P of y given x, which is the softmax of the decision variable. And you will see that is wrong, but is very confident. So he has 100. He believes that it's a cat, and his confidence is 100%. So he believes that it is a bird. So it's a fish, but in fact he believes that it is a bird, and his confidence is 95%. Or he believes that this is a mammal, but he believes that he believes that with a confidence which is 99%, and it's not a mammal. So which means that in many problems, so what has been checked or reported is that all these very amazing machine learning machine learning techniques have extremely high accuracy. For example, it's the same for object recognition or for image segmentation and things like that. They have extremely good accuracy, but when they are wrong, and they still report they are wrong with very and they are overconfident in their prediction. So they do not they cannot say that they don't know. Okay. So this can be quantified when you look at calibration metrics, so which can be the log likelihood or the Bayer scores. In the Bayer score, you compare on a test, on a calibration set, you compare the probability of observing one label minus the predictive distribution for this label. That's the Bayer score. Or one calibration metric which I like is expected calibration error, which is very interesting. In expected calibration error, you take a calibration set, you just divide the calibration error with you make a kind of histogram, okay? You count for each of these value, you count on the calibration data the number of time you have, and then you look at what you compare with confidence. Which is computed, the empirical accuracy with respect to the confidence which is predicted by the model. Okay, so the ECE, in fact, is on what you do. You compare you compare predictive accuracy on the validation set minus the confidence, and if you have, of course, a perfect calibration, then the empirical accuracy should be almost equal to the confidence. And what you display in general is the reliability curve, which is the difference between empirical accuracy minus confidence as a function of the confidence. When it is flat, it means that the model is well calibrated. When it is when the reliability curve predominantly lies above the flat line, which is where the empirical accuracy is equal to the predicted confidence, then you are either underconfident or overconfident. And what happens typically is that you are overconfident most of the time. Okay. So that's a problem has been identified for quite a long time. So as soon as people have done deep learning, they have noticed that deep learning lacks the error in deep learning is the calibration of error is wrong, and there are many approaches, and I will describe the approaches later on. But there are many approaches which have been developed so far, and one of these approaches is Bayesian. So what are the Bayesian inference promises in artificial intelligence? Is first to improve the predictions. Second is to obtain reliable uncertainty estimates, and also that you might do some model comparison, even if in the world of deep learning that doesn't seem to be very much applied. So you can compare base factor if you are willing to compare model, but the dimension is so large that it's not really doable in practice. And all these problems. Bayesian inference support active learning, continual learning. If you look at the continual learning literature, it has a strong Bayesian flavor, and also, of course, decision making under uncertainty, which as I said, it becomes more and more important, especially because people use AI for medical diagnosis, or also because machine learning techniques are able to take decision, and if you take decision, you are willing to have a kind of assessment of the uncertainty of your detection. So the Bayesian deep learning community is very active with many different flavors. When I look, the last time I looked at Google Scholar, there was 10,000 results on Google Scholar for Bayesian deep learning, so which means that you are much more on Bayesian stuff, but Bayesian deep learning is already 10,000 papers. And you can find application both from astrophysics to medicine, and also to advertising, click-through rate prediction, PDEs, active learning, and much more. So what you do in a Bayesian approach, it's a very simple-minded idea. So what you do is that you take the same trend set, you have a statistical model, typically the same statistical model. As I said, it would be a CovNet, a ResNet, or something more fancy, a UNet if you are doing image segmentation. what you do is that you take a prior on the parameter of this model, which are typically the synaptic weights and the bias. Sometimes you use a kind of fancy prior with different value, different prior for the bias term and for the synaptic weights. And then what you do, you compute you compute the posterior, you compute the likelihood of the data, so which is PD given theta, and using Bayes theorems, you simply write posterior distribution of the parameter given the trend set, okay, with Bayes error. And so in fact, what is the trick there? So you have two approaches in classical ML. You have a single base setting of the parameter, okay, which is chosen by minimizing train error plus regularization term. Whereas in Bayesian ML, the method infers a posterior distribution. So you are computing the posterior distribution of the parameters given the observation. And once you have this posterior distribution, you can obtain the posterior predictive distribution of y given x and the trend set, which is obtained by integrating the prediction py given x and theta that you integrate with respect to the posterior distribution of the parameter given the trend set. So this is called sometimes Bayesian model average. And the idea there is that you instead of course you will approximate this integral with a sum. So you will average over different sets of parameters. So this is what is called model average. So you average different value of these parameters. And what you expect is that you can combine complementary solution corresponding to different set of parameters. And this, having said that, it shares the same. So all the methods which have been used to do uncertainty quantification for DeepNet basically use the same type of techniques. So it's the same for deep ensembles. In deep ensemble, it's not at all Bayesian, but deep ensemble, what you do typically is that you combine the parameters obtained from different initialization, and sometimes it's not you share with some parameter sharing. You have all these techniques which are related to swag, or it's the same for MC dropout. MC dropout has a very, very specific flavor. It's something which is not very well known, but Monte Carlo dropout is also a way to obtain a kind of sets of parameters. Okay. Of course, Bayesian model averaging is challenging due to high dimension, the posterior which can be demanding, so it can be multimodal. The model structure is very complicated and the dimension of the number of parameters is just huge. And you also need to take into account, of course, computational and memory constraints. So if you look at, for example, a large language model, where you have several trillions, you have billions of parameters, or hundreds of billions of parameters. Of course, if you cannot accommodate 10,000 models of that size, okay, that will never fit. Okay, so there are many unresolved questions for BMA. So there are other solutions. I will present one solution. Of course, one solution which is very popular in Bayesian deep learning is to use variational approximation. To provide Gaussian approximation to the posterior. And in general, you use mean field. So there are several methods which has been done in that direction. So you can use Gaussian approximation or mean field approximation. So for mean field approximation, you obtain an algorithm which is closely related to back propagation. So it's called Bayes back prop. So it's a very simple one. You might have a multivariate Gaussian approximation, which have a different flavor. As I said, you can do Laplace, or you can do swag, or multiple swag, or you can use other techniques. Okay. So what I will use there is based on, it's more familiar to my Russian friends. It's based on the unadjusted Langevin dynamics. So what you do is the following. So you posterior. So you take the posterior distribution of the parameter given the trend set. You make some simple assumption. You assume first that it is locally Lipschitz, and you also assume that it satisfies some kind of coercivity condition. So which means that when you get far from the when theta and theta and their theta are far from the center of the space, this quantity are more or less log concave. This is the meaning of this coercivity condition. And under this condition and some other minor condition, you know that the Langevin stochastic differential equation is ergodic. And it's interesting to note that the posterior distribution, P of theta given D, the trend set, is a unique invariant distribution for this diffusion. Okay, so there is, it's a nice observation that under very, very general assumption, if you are able to run the Langevin diffusion, which is that Mother Nature does when you want to equilibrate, you use a kind of Langevin diffusion, and P theta given D becomes a stationary distribution of this diffusion. Okay, so it seems to be perfect. Of course, you cannot really run this Langevin diffusion, so you need somehow to use some kind of discretization. So there are the easiest way to do a discretization is to use a Euler-Maruyama scheme. So you simply use an explicit scheme for solving this stochastic differential equation, which is completely explicit. So there is no implicit step because the implicit step will be too cumbersome. And so you simply use the step size gamma, you compute the gradient at theta k, which is the current fit. Then you add the increment of the Brownian motion, which is square root of 2 gamma times a Gaussian variable in dimension d. And then you obtain like that recursion, which looks exactly like a stochastic gradient descent. And on the top of the stochastic gradient descent, you add some noise. Okay, of course. Well, they are better now, so just a side comment because I will not discuss that today, but it has been advocated that it can be more appropriate to use a better discretization scheme, and in particular, very recently, people have shown that semi-explicit Runge-Kutta discretization are much better, and in particular, the bias of Runge-Kutta discretization is much less important than the bias of Euler. I never look at that really, but it has been reported in a paper by Pereira. So perhaps it's a direction of research. I'm not sure that the theory is well understood, but in practice, apparently, the use of better integration schemes, better integrator is really worthwhile. So what are the properties of Langevin dynamics? So this is something which is known for quite a long time now, so 6 or 7 years. So we start work on that with Alan Durmus, and there are several, at that time there were several parallel work. In particular, there is a very nice paper, and I think it's better than us in when you look at the result, it looks better. It's a paper by Caragoulian and Dalalian, so which is perhaps easier to read. And if you start with very simple assumption, if you assume that some regularity conditions, that the posterior distribution is C2, that it is strongly convex, L smooth, then when you compute the Wasserstein distance between the low of theta k and the posterior distribution, there are basically two terms. The first term is kind of the way you forget the initial condition, which is 1 minus gamma m to the power k, k being the number of iterations, okay? And then you have some dependence in the dimension appearing in the norm of theta 0 minus theta star. And 2d over m is the variance of, is the norm of the Gaussian, is the expectation of the norm of the Gaussian variable that you read. And you have a bias term. The bias term, you have an explicit expression for the bias. The thing which is important to know is that this bias term is of order gamma under strong assumption, and from that you can obtain some kind of mixing rate. Okay. Okay, so that's what is known. Of course, in gradient descent, it's seldom used. It's like in optimization for many reasons, but because one of the main reasons is there is a computational bottleneck, because the gradient evaluation will typically scale proportionally to the number of observations, which becomes infeasible in the big data limit. So it has been proposed by Welling and Tay to replace the full gradient with stochastic gradient estimation based on mini batches. And this algorithm gives rise to the stochastic gradient Langevin dynamic, which has become, of course, the most important MCMC algorithm in Bayesian inference for large data sets. So the analysis and its finite sample performance has attracted many contributions, so Ma and Liwai and myself and Bros. And okay, so what we obtain is that the resulting estimate of the gradient is still unbiased, but the variance could negate the computational advantage of SGLD. And we had a paper with Sergey, Alex, and Denis Belomesny, which appeared in 2021. But in fact, we worked on that in Paris in 2019, if I remember well, spring 2019, in order to improve to reduce the variance of the stochastic gradient in stochastic gradient Langevin dynamic in order to correct the bias at convergence. Okay, so what are the approaches? You can use a type of SAG or SAGA. You can use stochastic variance reduced gradient. You can use spider method. You can use other variance reduction methods. So ask Sergey, so he knows a lot on that. Okay, so that what we know and what is so that is a common knowledge. Now we look at what is needed to extend this to the distributed federated setting. So what happened in what is particular to distributed or federated setting is that you have several workers, not a single worker, but several workers, and each several workers has a given data set. Okay. And so which means that the data, the overall data set is split among agents or workers, okay? So what is the difference between distributed and federated? So in distributed, data are typically centralized, and then the central authority distributes the data among the workers, and in particular what it does, it makes it sure that the distribution of the data in the workers are more or less the same, okay? But in federated, the data themselves are collected by agents, and this data remains local to agents, so nobody accesses the data except each given agent. So which means that there is no sharing of data, and in particular because the agents collect data differently, and they have different bias, different distribution. It means that typically the data of each user can be different from the data of the population. So there is a very different problem. The problem which makes distributed and federated very different. The first big difference is that in one case you have more or less, you can consider that the data are more or less ID, whereas in the federated case you have a huge statistical heterogeneity. And of course, you might have different constraints. It really depends. There are many applications of federated learning. Each have a different flavor. So there are some applications which are called cross-silo, in which case in cross-silo you don't have many agents. You can have something like 2, 3, 10 agents. And all these agents communicate at each iteration. It is called cross-silo. But privacy issues are, in that case, very important. Or on the other end of the spectrum of federated learning, you go to something which is called cross-device. In cross-device, the data is split among many users, like millions of users in some cases. Each user has a very small amount of data. The distribution imbalance can be extremely strong, so which means that you have a lot of statistical heterogeneity in general. And on the top of that, you have communication constraints, so which means that the bandwidth for each agent can be very different, and you have the bandwidth limitation can be sometimes very important. You might have a partial participation, so the agent might or might not participate to the sharing. So you have many different flavors that you don't have in distributed learning. Okay, but if you look nevertheless at distributed and federated learning, it's basically always the same type of question. So what you have so now you have the as you say, the likelihood are distributed, the data are distributed on B users. So what you can obtain is that you have each user have his own local, each user have his own local, posterior, okay? And so which means that you have a large number of users, okay? You have a large number of users, and this user have, and so which means that the posterior distribution, okay, becomes a product of the local posterior, okay? So which means, and in all this type of problem, you have to sample a distribution in which can be written as a product of local posteriors. So I will describe two algorithms. So there are three in the paper, but so we have three algorithms in this presentation, but I think I will not have time to go over the three presentation. It will give you a flavor of what we do. So the first one is based on a paper that has been accepted last year at ISTAT, and is based on what is called quantized Langevin dynamics for Bayesian federated learning. Okay. So how it works? Okay, so you have so in federated learning you have a central authority, which is called a server. Okay, so the server never accesses the data. The server accesses only the parameters which are shared. The only thing which is shared is the parameter of the model to be learned by the federation of learner or federation of agents, and the data are always kept locally by the users. Okay, so you have a server, central server, which has no data, and you have local user, and this local user owns the data. Okay, and what they do is that the server coordinates the learning. Okay, so at each iteration, what people do is that the local user reads the data from the local server. So it's kind of at each iteration, the server broadcasts a new value of the parameter. So it's a broadcast channel that each user can access. Okay. So then you have in the downstream you have the parameters are sent to the users, and what the user do they do some local processing, and what makes the difference between the different federated learning algorithm is that the way the local processing is carried out can be different, and at the end of the local processing there is on the uplink. The users send back the result of their processing, which can be, they can send back parameters, they can send back update of gradients or quantity like that, or some slightly modified quantity like that. I will explain what. Then the global authority, the server, mixes all this information and provide a new parameter updates or new update for the parameter. Okay, so there are two classes of methods which have been proposed more or less at the same time. So in 2017, basically the term federated learning was coined in 2016. So and these two algorithms, which are very, very simple algorithms, still give, in fact, the two. So there are many algorithms today, but there are these two algorithms, the two classical ones. The first algorithm is called federated averaging. It has been proposed by Matt Mahan, and it has been implemented by Google. In particular, it's used in a cross-device because it is used in particular to learn next word prediction. So the next word prediction used in Android is done in a federated way. And of course, you can understand that the next word that you use or that I use or that you use are different. So it means really the case where you have a kind of so we learn model, but we have also to learn that we are that the statistical distribution of words that I use and that you use are different. Okay, so that's federated. So the two techniques, federated averaging. In federated averaging, workers compute and exchange parameters, and the way, in fact, you just control the amount of communication in that each user at each round, each user can do several local steps, so several evaluation of the gradient. Okay, and in QSGD, so QSGD is more is kind of looks a bit like parallel LGD, if you wish, and the difference with parallel LGD, so which means that each iteration, the workers compute a new gradient, only a single new gradient. Okay. And then they transmit this gradient to the supervisor And in order to control the amount of information which is exchanged, you use lossy compression of the gradients. Okay, so I will discuss, in fact, first the way you compute the lossy compression. So what is a compressor? So we use compressors which are unbiased. So which means that the compressor, so it's not only a quantizer, it's a quantizer which has a specific flavor, and this flavor is that the quantizer should be unbiased. Okay, so typically the quantizer you should have a kind of extra randomness in the quantizer in order to make the quantizer unbiased. If you do simply scalar quantization or vector quantization, it will never be unbiased. So you need to correct that to obtain an unbiased quantizer. And this quantizer should have, of course, a certain quality, so it should reduce. So the norm between x and the quantized version should be proportional to x squared with some factor omega, which is more or less the efficiency of the quantizer. So one way to do this is to use stochastic scalar quantization. So typically what you do, you take a vector MRD, you extract the norm, so you can obtain, you will quantify the norm with quite high accuracy. And then what you do, you can also quantify you will replace C of xi, you will replace it by the norm of x, okay, times the sine of x, times some quantity which is equal to random variable, which may take two values when xi divided by his norm belongs to the interval L over S, L plus 1 over S, and you will, with some probability, you take L over S, with some probability, you take the other side of the interval, and you make it in such a way that this is a randomness, where the randomness comes from which point you select, and you make it in such a way that the expectation of this quantity is unbiased. And of course, the number of bits that you need to represent a value depends upon the number of division that you have used in sometimes people use simply 1 bit, so which means that you simply keep the sign of x, okay, plus the norm of the vector. And how work SGD? It's a naive one. So the naive one SGD, what you do is that you, in parallel, what you do, you compute theta k. So theta k is sent from the central server to the agent. The agents compute a mini batch gradient from parameter theta k, okay? Then go through the compressor. The compressor, you obtain an unbiased estimation of the gradient, and from this unbiased estimation of the gradient, you send this quantity to the compressed version of the mini batch gradient to the central server, which aggregates the gradient and computes an update for the parameter. Okay, seems to be very naive. In fact, it doesn't work very well, and it doesn't work very well because the quantization error remains large. And why it remains large? It is because at convergence, of course, the gradient of for each individual client is not going to 0, okay? And the norm of the compressed gradient can be large, okay? And because the norm of the compressed gradient can be large, and remember that we have assumed that the compressor, the difference between x and C of x scaled like x squared, because of the norm of the compressed gradient can be large, it means that you will have at convergence a rather large error. Okay, so there is one ID, which is really a signal processing ID, which has been done by Horvath in 2019. And the ID, and it's really like a signal processing ID, where it is what is used in telecommunication for adaptive DPCM, so ADPCM, so adaptive digital pulse code modulation. It's exactly the same ID. So what you do is that you obtain for each user compute a memory term, okay, eta k of I, and what you transmit, you don't transmit the mini batch gradient, you transmit the mini batch gradient minus eta k I, okay, and this quantity should predict, in fact, this quantity. So which means that you expect that this quantity is much smaller. The norm of this quantity should be much smaller than the norm of this quantity. Okay, and doing so, the guess is that you will reduce the transmission error. Okay.
So eta ki is a kind of control variable, yeah.
It's a kind of control variable which is computed locally by each. It's computed locally by each agent and is never transmitted. Okay, I will explain. So so what you do on each clients, you compute mini batch gradient minus eta ki, you compress it, okay, with this compressor. Then you update locally this memory term, eta k plus I, ek plus 1I, okay, so this is the update term. You have a kind of leakage alpha. It's exactly the same in DPCM, otherwise it becomes unstable. You don't transmit eta ki, okay, and what you do on the central server is that you update according to this gradient, and then you compensate with respect to an eta k, and this eta k is simply updated using this update, okay? And if you look, of course, if you sum this update over I, okay, you will see that the update eta k at the central server, you don't know eta k plus 1I, okay? But you know the sum of eta k plus 1I, and this is exactly what you have there, okay? So which means that you don't need, simply using this, you obtain, so there is no need to transmit local memory term, okay? So this gives you the first technique. And then you can have also other address reduction. So doing so, in fact, we can define what is the first Langevin diffusion, okay? So now instead of using the gradient, what you do is that you simply use the gradient plus some noise, okay? So what you will do is that what we call the QLSD, the first algorithm is simply like QSGD, so that you typically replace the gradient that you compute on each client. The mini batch gradient is replaced by a compressed version, okay? And you add some noise on the server. So of course it's very closely related to QSGD. It's clear to understand that. You can do a first analysis. So assume that you have strongly convex, bleaches, compressor which is unbiased and which satisfies this error. And then what you need, it's a condition that we have used with Sergey already. We use what is called co-coercivity for each. So UAG is for client E, and you look at the G data, and you assume that you are co-coercive with coefficient M tilde. In fact, it's automatic when you are Lipschitz. It's simply to have the good constant there. Okay, so it's in fact when you are simply convex and then Lipschitz, you are already co-coercive. So if you are strongly convex, it's even better. Okay, and what we obtain a Wasserstein distance, and the Wasserstein distance looks a bit like that. So there is a part, the first part, which is there is not much surprise. It's a way you forget the initial condition. So it looks a bit like what we had before. So we have the strong convexity constant, which plays a role there, plus something which is a Wasserstein distance between the law of theta 0 and the posterior distribution. And then you have two other terms. The second term is due to heterogeneity discretization error. And in that case, this term is very annoying when you do the simple algorithm, because this term doesn't go to 0 when gamma goes to 0. Okay, this term doesn't go to 0. Okay, and then you have a term which is less annoying, which is a term which is gamma square A gamma sharp. Gamma A gamma sharp is bounded, and so this term goes to 0 as gamma goes to 0, and this term is due to the mini batch and the compression factor. Okay. Okay, so the sketch of proof is not a big surprise for people which have looked at this right in the A's. It's like you use a kind of coupling. Are you surprised, Sergey, or no? It's not surprised. So you couple, so you use you make as if you run a kind of diffusion on each, and then you compare with. So you use a coupling with the diffusion, and so there are some tricks, of course, to perform, but it's not a very big deal. And so you have additional terms which come, in fact, to these discretization errors. So it's not a big deal. So then what you can do variance reduction, okay? Because as I said, this is when you take gamma, which is of order 1 over n. So the problem is that this doesn't go to 0. So you might use variance reduction, and you can use, I will skip this one because I'm already running out of time, but at the end of the day, we have our best solution, in fact, couple two things. So it couples variance reduction, okay? But variance reduction is already important for mini batch Langevin diffusion. So it's you need to have some variance reduction. So the variance reduction is done in the SVRG style. You don't need to go to spider, so that you don't need to go to more sophisticated, I would say, variance reduction schemes. Then you have this memory term, okay, and then on the top of that you add HKI, which is another control variance, okay. And doing so, you obtain, you more or less obtain the optimal solution. In particular, you just using this control variance and using these memory terms, you more or less cope with heterogeneity and also to the fact that the gradient of each client doesn't go to zero. So this gives an illustration. It's not a very simple, not a very difficult one. So you start with NIST. And what you do to create the imbalance, so you take NIST, we have 20 clients there. So what we do is that each given client have client one has 70% of one, okay, and otherwise he had kind of we complete with the others have population distribution. Client 5 has 70% of 5, okay, and otherwise it's a population and so on. So, okay, so that's exactly the way we proceed, okay? So which means that we create heterogeneity in the sense that some clients have much more one label, which is overrepresented by far. And if you do simply, this is SGLD, so it's stochastic gradient descent, okay? That Q, that I have different version of QLSD, okay? And you see that you don't lose much in terms of accuracy, but you improved a lot in terms of Bayer scores and so on. So you increased a lot. So it's that stochastic gradient descent. It's not SGLD, it's SGD, okay? And you see that the expected calibration error is much better for QLSD. So it's much better there, okay? And NLL also it's much better. So that's and this is exactly what we obtain at the end. So when you look at, as I said, that's accuracy minus confidence, we should be ideally flat. So it's not exactly flat, but it's much better than for our QLSD plus. Is much better than for example, FSGLD, which is displayed there. So we improved a lot. It's not completely perfect. So when you look at when the confidence is very high, we still have the problem there in the curve. So and we are still a bit overconfident. We are less overconfident, but we lose 10% of overconfidence. Okay, so but we are still a bit overconfident because when you look at the accuracy curve, it's a bit too strong. Okay, so it's also interesting to see when you do out of distribution. When you do out of distribution, you will see that the predictive entropy, so that you obtain with the different methods and that the predictive entropy when the input is something which is taken from fashionist. So which means that it's clear in such case that the entropy when you are out of distribution, the predictive entropy is much higher. So which means that clearly means that it's good in the sense that when you have something which is not at all in the trend set, the predictive values are spread over different level. This is what you expect. Okay, so that another possibility which has a very different flavor, which is called DGLMC. So it's more for distributed, but of course it can be done in a federated way. And in a federated way, in fact, it has been done for Neurips. So DGLMC was in ICML 2021, And then it was, we had a kind of personalized version. So we use it also in a federated way to do a personalized model. And with Nikita Kotolevsky and Maxim Panov. I will not explain that, but it would be another presentation. But what is idea is that what you do is that same techniques, same problems, you are willing to sample the target distribution, which is a product of local posterior. Same techniques, each worker have only access to individual dataset DIs, you have to cope with communication bottleneck, and the idea is how to create a distributed algorithm. So the idea, in fact, the key idea comes from a paper by Maxime Vonneau. So Maxime Vonneau was a postdoc there, so he was in Lagrange for 1 year, and he did his PhD with Pierre Chenet and Nicolas Daubijon. And what they use something which is quite classical in Bayesian analysis, is that you do introduce auxiliary variables. So it's an idea also which you can find in optimization. So what you do is that you extend, you take auxiliary variables. So I call these auxiliary variables are called ZI, okay, and D1, DI, DB are the local data set. And you use a kind of graphical model which can be written like that, okay. So you start from theta, and then you replace, in fact, the local, you introduce the local posterior. So now you have the prior on the parameter theta, okay. Then you have, you introduce a kind of instrumental prior for the conditional distribution of the Zi given theta, okay. I will explain how we construct this quantity, and then you have a kind of local likelihood for given parameter Zi. Okay, so what is the elementary choice that we do is that we take for this distribution, for Zi given theta, we take the normal distribution with centered at theta with some variance which is rho I time identity. Of course, we can take something which is more complex, but typically what we do there is that we assume that all the local parameters of Zi are the parameters which are local to each user. And what you assume is that this local parameter should be close to the population parameter, and this parameter y tune, in fact, how close you should be to the global parameter. Okay, so at the end of the day, what you need to do, you need to compute, in fact, the joint posterior, so which is a joint posterior of the global parameter theta and all the local parameter which are Z1, ZB, given parameter D, and which is also is this particular product form is a product of local prior multiplied by the local likelihood, so it's parameter Zi, and now on the top of that you have the conditional distribution of Zi given theta. Okay, so which is called the Erding prior. Okay, and then what you do is that you perform it as a Gibbs sampler, and you use a kind of factorization which is inherent to this graphical model. So given at iteration t, you have theta t minus 1. You will update in order to obtain ZIT. So you update this quantity by sampling from this distribution, and this distribution depends both on the local likelihood and also it depends also on this posterior distribution of Zi given theta t minus 1, which measure how far you should be from the global parameter. And if you look at this, in fact, of course it depends upon theta t minus 1, but otherwise it's entirely local. So in terms of Zi, so given theta t minus 1, you simply have to update Zi. Okay, and then on the central server, what you do is a consensus step, and this consensus step, the good thing is that this consensus step, which is a distribution of theta t given Z1b to the power t, this consensus step does not depend upon the global parameter. So the consensus step is independent from the local data. So it depends only upon the local parameter, but not on the local data. So which means that the important point there is that the server update does not require to know the local data set. Okay, so the local step, you can perform them with Langevin dynamics, but you have to perform the Langevin dynamics on this spatial distribution with the product. So which means that in the Langevin step, you will have something which depends locally. It depends locally on the local parameter. Okay, so it's a gradient of the likelihood, and then you have a second term which depends upon the Erding distribution. So which makes where you have to make sure that your local parameter does not deviate too much from the population parameter. And then you add some noise, which can be correlated among users. Okay? And what you do on the central server, you compute, you do that ni times, so which means that you do several Langevin local steps on each users, on each agent, and on the central server, you perform the Bayes steps, and the Bayes step is completely explicit in that case. Okay, you can do a non-asymptotic theoretical analysis under always the same type of assumption. You may decompose the error in different factors. So you have what is called the Erding error. Okay, you have an error which is linked to the Langevin discretization, and there is something which is linked with algorithmic efficiency. And what you obtain at the end of the day, so it's not optimal. So we have found a way to do a little bit better, but it's not implemented in these bounds. So you have an explicit dependence upon rho, gamma, and the parameter t, and you can improve that. So it's not optimal. So we have better result now, but we don't have time to update. So that gives you, in fact, the result. Okay. Okay, so it checks. So you obtain the dependence in dimension, which is polynomial, and then you will see on this example that so in this example it's just an illustration. I don't. So if you take that examples of data which are taken from NIST, so it's typically when you do in NIST you do, if I remember well, something like 90. So it's easy to do something like 99% of accuracy, or even more than that. And in fact, when you look at the errors that you do, these are typically the digits where you make errors. Okay, so digits like that, which is not clear what is it exactly. So perhaps it's out of distribution. I think it's not clear what is it, or so you have some digits which are, this should be a 2, but it's not completely clear. This should be a 4, but it's not completely clear. And and you see there with DGLMC compared to DSGLD, you see the difference of distribution. So you see that our distribution is so we have much. So we have a large variance, so it's we are able to reproduce. So we have doubts on. So we say this one. So we say it can be a 2, it can be a 8, something like this. Okay, and then I will skip this one. So this one is the last one, which has been published too. So I think this one is very. So it's our last, and that's the end of the series. It's on federated averaging Langevin diffusion, where we do a kind of it's really a federated algorithm, and it's kind of extension to Langevin diffusion of federated averaging. So this is what we call it FAD for federated averaging Langevin dynamics. But okay, so I've been already too long, and I will stop there. So thanks for your attention.
Okay, Eric, thank you very much for your talk. So if you have any questions to the speaker?
If you are not completely killed.
Yeah, maybe I have a question. So in general, as far as I understand, people typically do exactly stochastic gradient Langevin, yeah? If they want to combine somehow this federated setup with Monte Carlo. Just because, you have an opportunity to compute stochastic gradient, you don't need full gradient. But are there any alternatives to SGLD? I mean, if people do...
Yes, they have. So, of course, what are the techniques which are used in federated learning? So there are techniques based on variational approximation. And one technique which seems to be very promising, and is a technique used by Google, is FedEP. So it's federated expectation propagation. They did not do much theoretical analysis, but apparently it works very well. So it is a paper by Eric Xing, Matt Hoffman, so last year, Andrew Gellman. So it's a paper which appeared in the last NeurIPS. The RIPS last year is FedEP, so it's really expectation propagation, okay? Which is a kind of it's variational in some way. It's not exactly variational inference because they use MCMC step, but they update. It's a way to update variational approximation, basically, but not using the classical elbow method. It's more like it's a technique which is more based on the on the reverse KL instead of the forward KL. Okay, so it's and you update what they call expectation propagation. You update a kind of variational approximation of each local posterior, which is Gaussian, multivariate Gaussian, with evidently some structure. And this seems to be quite promising. In particular, it seems to be very good in presence of statistical heterogeneity. And yes, so that there are all this method at least which has been used. I think other methods which have been used in the statistic quantification are deep ensemble. So you have federated version of deep ensemble, differentiated version of variational inference, of course. There are many papers in this direction. So you have many versions, many attempts in this field. Yeah, it's not the only possible method.
Yeah. I see. And then if they have reverse scale, then they need to do MCMC, yeah? Because
they do MCMC locally. Yeah, they have reverse scale and they do MCMC locally, and they use Gaussian approximation. But apparently, so they report in fact results which are very, very impressive because they do federated learning on super large models. So they use federated learning on billions of parameters and. So they do that on YOLO method and things like this. So they really played. So compared to all we have analyzed CIFAR. In fact, for DG and MC, it's the one for which we have learned the most of the simulation. We did CIFAR 100, but we never do YOLO. And so if you look at this paper on FedPE, federated expectation propagation, they look at very, very large models.
I see. Thank you.
But there is no theoretical analysis yet. It's not clear why it works well. But
it's interesting. I think it can be, I think that for theoretical analysis, it can be. If you remember, it was a paper by David Blay and his band on Markov score climbing, where they
it will be. I think it's interesting because they did not do any analysis, but the results are very promising. But they did not do any kind of analysis. Yes, and apparently there is something which because the big annoyance in practice in federated learning, the big annoyance is really the statistical heterogeneity. If you do it naively, so even not Langevin dynamic, but you do federated learning in naive way. You take NIST and the best accuracy that you obtain is 70%. So you degrade, and whatever the choice, so you really need, in order to retrieve the same accuracy, even when you are not doing Langevin, but you are simply doing gradient descent and things like that, in order to obtain 99%, you really need to make a lot of stuff like control variance, local variable, and things like that. So you really need to be careful. Okay, so it's not the naive way; it doesn't work. In fact, this is what you have to. That's a takeaway message. So the naive way doesn't work when you have a lot of statistical heterogeneity. except if you don't have a compression, of course, if you do parallel SGD, one step. So in cross-silo, in fact, they don't have that problem because in cross-silo, what they do is typically they simply do a gradient. Or token algorithm, I think, is not affected. If you look at the token algorithm that we have discussed, I think token algorithms are not affected by statistical heterogeneity. Not the same that QSGD or federated averaging. So token, I think, would be candidates because one topic which has not at all been considered yet is also asynchronicity, because here we analyze only synchronous protocol.
Yeah, but here you need to synchronize exactly after
each. Yeah, but you can do asynchronous in the sense that you can still have a central authority, but the central authority may, for example, interrupt. So it asks the result and it might interrupt the calculation of some user which lag behind. So there are several techniques you can do, and there are not much is known for Langevin in this direction. When you do, for example, there are Fed-async, so Fed-async algorithm or QFALD algorithm. So there are many algorithms which have been proposed recently for parameter estimation in a synchronous case, but centralized is not fully asynchronous like token. But so there is a central authority, but there is so the speed of users might vary, and in such case, it's yes, it differs.
Okay, so any other questions?
One in the chat.
Yep, it's a question about it's about it seems to be more about like medical applications. Regarding mentioned medicine, what are the methodological differences or similarities between innovative ML and traditional biostat modeling?
But in fact, it's so in medicine in general, they are so we collaborate with a French company called Hawkins, or OWKIN. And in fact, they are not using necessarily deep learning models. They can do federated learning with classical population models, and so it's not necessarily deep. They also have deep learning applications. There is they share recently, last year, they share in NeurIPS a kind of several databases for federated learning with several applications. It's called Flamby. Perhaps you know Flamby. So Flamby is for French is funny because I'm not sure it's funny for the others. So it's called Flamby.
It works, but a bit strange.
Yeah, so it's called.
You will see some part of the words.
Okay, so it's works now. Okay, so it's called Flamby. Okay, and the society is Hawkins. Okay, and they just and they deliver several examples. And it's really cross-silo, so it's a different flavor of cross-silo. So a lot of statistical heterogeneity because it's different hospitals typically. So different hospitals, they have different pathologies, so they don't have the same population, they don't have the same techniques exactly. So the data are heterogeneous. There are several differences in the distribution of the data. You have medical data, you have imaging data, you have diagnosis data, a lot of data like that. A lot of statistical heterogeneity, but cross-silo, so the number of agents are small, so it's most often less than 10. They don't have bandwidth problems, so they don't use compressor. But they have a lot of something I did not discuss because I did not work a lot on that. I did not discuss privacy. So there are also a lot of things which are linked with doing Bayesian analysis with privacy. So in Hawkins, they look a lot at the privacy issue. they do secure aggregation, they do secure multi-party computation and things like that, because the privacy of user data is very important. Otherwise, so federated learning is more, you don't change the model. So federated learning is a way to perform computation where people, agents are willing to learn a single model, which can be a population model, of course, but using several data sets, and the data sets are never disclosed to the community. So all what you are willing to disclose is some updates of parameters, and even when you release a parameter, you might want to have some privacy guarantees.
Okay, thank you very much for your answer. So I think that we are now a little bit out of time. So I suggest to stop at this point.
Okay.
So, let's thank our speaker, and I think that we are done for today. So,
okay, thanks a lot, Sergey. Thanks a lot, HD Lab.
See you.
See you, bye-bye.